At the raw network layer, the Internet Protocol operates entirely on a best effort basis. It strictly routes individual packets from one IP address to another, but it doesn't check if they arrive in the correct order and offers no guarantee they arrive at all. Relying on this raw routing is insufficient for modern computing. Applications require structured, predictable data streams to function without crashing or returning errors. This creates the need for a logical bridge above the Internet layer, the transport layer. It manages end-to-end communication between hosts, handling the complexities of session establishment and data segmentation, shielding the application from the physical inconsistencies of the network. This introduces a core engineering tension. Different applications running on the same device have mutually exclusive network requirements. One might require perfect accuracy for a file transfer, while another needs instant delivery for a voice call. The transport layer resolves this tension by multiplexing traffic and offering two specialized transmission engines, TCP and UDP. A modern workstation routinely runs dozens of network applications at once. Web browsers, file transfers, and background system updates all compete for bandwidth. An IP address alone cannot manage this. It only delivers data to the correct physical machine, not to a specific application instance. To solve this, the network uses a port number, a logical identifier that routes incoming data to the exact application that requested it. When you combine an IP address with a port number, you create a socket. This pair serves as a unique endpoint identifier for a specific conversation. Consider a single client machine initiating two separate communication streams to the exact same server. The client directs web traffic to destination port 80 and file transfers to port 21. To track the return data, the client generates temporary, randomized ephemeral ports for its end of the connection. This socket pairing is the mathematical mechanism that enables conversation multiplexing over a single physical network interface. When an application requires total data integrity, where a single missing packet could result in a corrupted database or a failed financial transaction, the transport layer employs the Transmission Control Protocol, or TCP. TCP is connection-oriented. A formal session handshake must be completely negotiated before a single byte of application data is transmitted. Maintaining a reliable connection requires significant overhead, reflected in the 20-byte TCP header attached to every segment. The sequence number field perfectly reassembles out-of-order data, while the acknowledgment number field creates a continuous feedback loop, confirming successful delivery back to the sender. If an acknowledgment isn't received within a timeout period, the protocol automatically retransmits the segment. Furthermore, the window size field provides dynamic flow control, telling the sender exactly how many bytes the receiver can accept at once, preventing resource overload. Because of these safeguards, banking systems, email servers, and web browsers rely on TCP to ensure that every byte arrives exactly as it was sent. TCP deliberately sacrifices transmission speed to guarantee the mathematical certainty of data delivery. The alternative is the User Datagram Protocol, or UDP. This is engineered for applications that prioritize immediate delivery over perfect reliability. UDP is stateless and connectionless. Data is fired into the network immediately, without any prior handshake or resource negotiation. Removing the tracking and sequencing fields slashes the protocol overhead from 20 bytes down to a mere 8 bytes. Without sequence numbers, UDP applications process datagrams in whatever order they arrive, even if mixed up. This is best effort delivery. If a packet is lost in transit, UDP offers no acknowledgement and never attempts to retransmit the missing data. For real-time communications, this is an engineering advantage. In a live video stream, waiting for a retransmission causes lagging or frozen frames that are more disruptive than a momentary drop in quality. This makes UDP the standard choice for VoIP telephony, live video streaming, and rapid DNS queries. The architecture deliberately removes reliability features to achieve the lowest possible latency across a network. This chart shows the transport layer sorting traffic. The trade-off is clear. TCP accepts higher overhead for guaranteed delivery, while UDP risks data loss for speed. Applications choose based on need. Web browsing requires TCP, while live streaming relies on UDP. This layered abstraction simplifies the development process. Software engineers do not have to manually code data segmentation or complex retransmission logic into every individual program. An application merely passes its data payload to the designated socket, relying on the transport protocol to execute the appropriate delivery strategy. Network architecture is defined by these trade-offs. TCP ensures the data is perfectly correct, while UDP ensures the data is delivered immediately.